Greetings, chemists. This video is going to be a lecture on reaction rates. What do we mean by the rate of a reaction? Well, generally rate is about speed. So let's suppose you had a big container of molecules, molecule A and B, and they're all swimming around in the same drink, and they're going to react with each other according to the following equation. Let's suppose molecule A reacts with molecule B to produce molecules C and molecule D. Well, this can happen quickly or this can happen slowly. I mean, every now and then one of these A's is going to bump into one of these B's and they will react and we'll get some of this. And over time, if we looked into this solution, you might see that some of these had gone away and some of these are starting to appear. And if we timed it, if we got out a stopwatch and measured, we would find relative strengths of each of these. So oftentimes the way this is calculated, especially in aqueous solutions, is as a concentration in time. So they would do delta. The term for concentration, we often use brackets, so like the concentration of A over time could be a way to measure the rate of this reaction, or that would be the rate at which these A's are disappearing. So if we looked, let's suppose, I could throw some numbers at you. Let's suppose that we had a 1 molar solution of A at the beginning, and we wait 10 seconds, and then we look again, and it's a 0.5 molar solution of A. Well, the delta means the change. So the change, we went from 1 molar to half molar. That's a change of a half molar, or actually it's a change of negative half molar because we lost some concentration of A. So on top of this equation, we would say we lost half a molar of A, and we did it in 10 seconds. And if you divide that, you would get something like minus 0.05 molar per second based on chemical A. And you could do similar concentration checks with C and D. But what we're basically doing is counting up or measuring the amount of molecules or moles per second that these things are changing by. Okay? Now the theory is that in order for these molecules to actually react, they have to hit each other. All right? This is known as the collision theory. So if you've got several reactants, A and B, floating in the same drink, they actually physically have to come into contact with each other in order to react. If you just had two trays, one of A molecules and one of B molecules, and you never mix them together, there's not going to be any collisions and they're not going to react. Now, how can we adjust how fast they are reacting with each other? How can we influence the rate? Well, suppose I have this situation with A, B, something like this. Okay, these are my chemicals in a solution, and they're going to bounce around. Remember, there's random motion for all molecules within like an aqueous solution or gases in a gas cloud or anything like that. So if all these chemicals are floating around in the same solution of water, eventually they will hit into each other. If I want to make that happen faster, one thing I can do is put them in a smaller container of water. Let's suppose that I only fill the water up this high, but I use the same number of molecules like this. Now you can see they're all much closer together here. They have a lot less space. And by that token, they're going to hit each other more frequently, and those collisions will happen more frequently, and that reaction will go faster because I'm increasing the rate at which they smack into each other. And every time they smack into each other, there's a chance that they, undergo this reaction and turn from A and B into C and D. Now, what did I do? I reduced the volume of the solution, or I increased the concentration of the solution. So increasing concentration has a tendency to increase the rate of the reaction. It increases how quickly A and B combine and form C and D in our little fake reaction here, okay? So that's one way we can deal with it. All right, what's another way we could do? We could alter the conditions to make the reaction happen faster. Well, one thing you could do, let's suppose you had that same original beaker with the A's and the B's in it, and we light a fire underneath it, or we put it on a hot plate and we make it really hot. Now, you remember from the temperature chapter that the heat of a solution is about how quickly the molecules are moving. When you heat up a solution, you make them bounce around faster. And the faster they're moving, again, the more times they're going to hit into each other, the more times they're going to collide, the more collisions will happen at the higher speed, and the more the reaction will go forward, or the faster the A's and B's will react and form C's and D's. So increasing temperature will increase the rate of the reaction. All right. What else can we do? Let's think about, I was going to draw, well, I'll do both. Let's think about a glass of water into which I put one giant ice cube. A kilogram worth of ice, let's suppose, and I put it into a big old glass of water, and I watch how quickly it melts. Now imagine in the second glass of water, same size glass of water, same amount of water, and I put in a bunch of little tiny ice cubes. But it's the same amount of ice. And I ask you which one should melt first. Now, this is not a great example because melting is not a chemical reaction. But you would probably expect that the little ice cubes would melt faster than the big ice cube, even if they all have a total mass of 1 kilogram. Basically, because all the water can get into the cracks and attack them from all sides, whereas here it can only get to the outside edge, and there's a lot more on the inside that's sort of insulated. An actual chemical reaction comparison would be something like a log of wood. Suppose we had a log of wood, and you put a match underneath it, and you try to light it on fire. You try to burn up the whole log of wood. And we ask you how long it takes the log of wood to completely burn with this flame source. Then, imagine we have the same amount of wood. Let's say this is a kilogram worth of wood. Let's say we take that log of wood and we shred it into little tiny pieces. But it's all the same mass. We don't lose any pieces. We just cut them up. And then I take that log of those pieces of the original log that are still 1 kilogram worth of wood, and I try to light those on fire, and I see how long it takes those pieces to burn. Well, this would actually happen a lot faster. And you can kind of think about it this way. Wood is like mostly carbon. And when wood burns, and hydrogen as well, when it burns, all the oxygen in the air comes in and attacks. And if we think about our collision theory of chemical reactions, every time an oxygen molecule bounces into that log of wood, it has a chance to react with it and catch it on fire. Well, look at this. I can only hit this log of wood from the outside, and there's so much on the inside. There's a very small, only a little bit of surface area that's actually exposed. Most of it is actually shielded. Well, here, if I look at this, there's all this extra surface area where oxygen can come in and attack each of these little pieces. So by increasing the amount of places where molecules can attack, I make this reaction happen a lot faster. The little chips burn a lot faster. This is why if you ever go out in the woods, like you're camping and you want to build a fire, you start with little twigs and things because they have a higher surface area ratio, and you only put the big logs on later. Now, the big log is nice because it'll burn longer and you can leave it in the fire. And that's because it's going slowly because only the outside edge can burn and the inside has to wait its turn. Okay, so increasing surface area will increase the rate of the reaction. Cool. Let's talk about other types of reaction. Suppose you had some gas particles, and instead of doing like before I did the beaker, but this time if you were using a gas, you probably put it in like a balloon. Suppose I fill up a balloon, and I fill it up with two of our favorite gases, some hydrogen and some oxygen. You use a hydrogen tank to fill it with hydrogen, then you fill it up the rest of the way from an oxygen tank, assuming it didn't immediately explode, which it might. But assuming you could do this, let's imagine a situation where you have a balloon filled with these two types of gases, and we know that hydrogen gas will react with oxygen gas, and it will turn into water. Okay, and we have all, this is again by our collision theory. We have these hydrogen molecules bouncing around. We have these oxygen molecules bouncing around. And anytime the two bounce into each other, there's a chance that they have enough energy to combine and to form water. How can we affect the rate of this reaction? Well, we can do a lot of the same things we used to do before. We can make the size smaller so they're more concentrated. We could heat it up so they're moving faster. What we could also do, and then I guess this is sort of related to the size issue, is we could squeeze them. Imagine that we increase the pressure on those gas particles. Unlike solids and liquids, gases will respond to changes in pressure. Because they have so much space between them, they can be compressed. So if we squeeze these objects, by adding pressure, we can make them collide more frequently. All right, pressure is actually oftentimes the definition of the pressure of a gas is based on how often it collides with itself and with the walls of its container. So a higher pressure means more collisions. And by our collision theory, more collisions would lead to a faster reaction. We would create water faster. So increasing pressure of a system of gases, this only works for gases, will increase the rate of the reaction. Okay. And there's one more thing we can do that I'm going to talk about here, which is adding a catalyst. And catalysts are a special kind of molecule. Here's how I can sort of explain it pictorially. Suppose you had two atoms or two molecules, one shaped like this and one shaped like this. And when they react in a specific way where they fit together like a jigsaw puzzle, and they turn into, right? You can see how that would fit in. They turn into that new molecule, but that's the only way, right? The one side has to bond in a specific way so that it fits just like that. Now, you could imagine by collision theory that this is not always easy to accomplish. Let's suppose that they come in like this, like they're moving along, and this guy's moving this direction, and this guy's moving this direction. And when they hit, they just kind of bounce off of each other because they're not in the right position to fit, to line up, right? And this happens a lot in chemical reactions. If the molecules are not in the right orientation when they collide, the theory is they don't react. They don't complete the reaction, right? until they finally bounce around and flip until they finally happen to be lined up in the right exact way, just like this, so that they can react and bond, okay? Well, a catalyst is a molecule that kind of makes that happen. Suppose that the catalyst had like a little arm here, and it could hold on to this atom in such a way, and it could hold on to this atom in such a way that it always faced them in the right direction, so that when they were coming towards each other, they'd fit right in. Your body actually produces lots and lots of catalysts so that it can accomplish certain chemical reactions within your body that you need for life at the speed they need to happen. So if you had a chemical like this floating around amongst all of these reactants, it would help smush them together. One interesting thing, suppose this is the chemical, let's say it's like a little triangle. Once these two react and form your product, this guy would detach and would go off and find another pair. So you could actually use him more than once. So often the way we define a catalyst is we say it lowers the activation energy of the reaction. But it's not used up. And this is helpful because you can have, you're limiting and excess reagents in terms of these two chemicals of the participating chemicals, but you need only a very little amount of the catalyst because it never gets used up. It just kind of pushes them together and moves on. It's not changed by the reaction, whereas as soon as these two guys get together, they're gone. They've turned it into something else. Okay. Lowers activation energy. If you remember from our energy video, the activation energy, right, would look something like this. So if you had a heat, an energy over time, or an enthalpy graph, you have this activation energy here. If a catalyst was in the reaction, the curve looks something like this. It takes that activation energy and it makes it a lot easier to hit. Okay? So those are some factors, the factors that we're going to be dealing with that affect the rate of a reaction. We have that reactions have to collide. Chemicals have to collide in order to react. We have that if you make it at a higher concentration, they will react faster. If we have it at a higher temperature, they will react faster. We have that pressure will help if it's a gas. We have that chopping it up or using a higher surface area will help. And that a catalyst can lower the activation energy and make it all go faster.